Oh, now
Hi.
you took over as the host, right?
Yeah, because I need to start the video recording.
Yeah, I saw it would be automatic.
Well, it just for it to go on YouTube immediately, then it's not automatic. I kind of have to do it manually. How is everyone doing?
Very well. I don't know, but I'm answering for everybody, which is probably wrong.
Yeah, fine with me.
All right, so it's probably time to start. So we are very happy to have today Chiara Esposito, who will be speaking on deformation and Hochschild Cohomology of Coisotropic Algebras.
Yeah,
Chiara,
my name is.
I give you the floor.
Thank you. Okay, so let me start. So first of all, I'd like to give you a rough idea of what the talk is gonna be. So as Anton introduced me, I will talk about deformation and Hochschild cohomology of coisotropic algebras. And this is a presentation based on two papers, essentially, both joined with Marvin Dippell and Stefan Waldmann. And there is, a final part of this talk that it's really about our ongoing project. So I want to try to show you a little bit what we are really working on and what's the ideas we have in mind for the future. So a very short table of content. First, I need to tell you what a coisotropic algebra is. And the idea, essentially, I will go, of course, more into detail about that, but is to encode all the information of reduction into an algebraic notion, which is coisotropic algebras. And then what we want to do is study deformations of coisotropic algebras. And this is done in the usual way, in some sense. So via a suitable DGLA that we have to define. And then we really go into the theory of deformation of coisotropic algebras, which is somehow similar to the theory of deformation of associative algebras. That's why we mention Hochschild cohomology. And finally, I will tell you what's going on with the HKR theorem, because this is still work in progress. We have already some result. So I can tell you a little bit the state of the art in some sense. Okay, but let me first start with some rough ideas. So let's say the keywords are deformations, Hochschild cohomology, coisotropic algebras. So let's start with coisotropic algebras. So the idea, as I told you a little bit already, is to introduce a more algebraic approach to reduction that somehow recovers both classical and quantum situations. And the motivation somehow comes from Dirac ideas of quantizing the first class constraints, which are generally described by a coisotropic submanifold, and obtaining a quantized version of a coisotropic reduction. So when I talk about classical system, classical mechanical system, I have in mind, of course, a Poisson manifold or a Poisson algebra. And when I talk about quantized system, I have in mind formal deformation quantization at the moment. So really formal deformations of these commutative algebra. Okay, so this is, let's say, the idea, the motivation. So we have to define these new objects, the coisotropic algebras, which are consisting of triples of algebras, and these triples have to encode all the information we need for reduction. I will show you how. So second step, second idea, deformation. So again, we have now our algebraic description of reduction, and we want really to cook up the corresponding theory of formal deformations. And how we do that? Classical principle, deformations we know are governed by differential graded Lie algebras. So what we have to do is really to understand which differential graded Lie algebra is associated to coisotropic algebras, and then we will see that formal deformations are actually described by Morer-Cartan elements, as in the case, as in the, yeah, I will say in the usual case. Then we have to understand what does it mean equivalent deformations. And this will allow us to somehow look at equivalent classes of deformations of these algebras. And you understand that since coisotropic algebras contains the information of reduction, these deformations are somehow, well, let's say, suitable to describe the deformation and reduction diagram.
Chiara, so there are people on the chat who are saying that maybe we don't see the bottom of your slides. Could that be true?
The bottom?
On this slide, the last thing that I see is, oh, okay. Yeah, you can see the last line I only see now, so you would need to move them when,
yeah, okay.
When you come to it. Thank you.
Okay, so we have, as I said, equivalence classes of deformations, and we want to study the compatibility of deformation and reduction. And the fact that we have in the algebra already the information of reduction, of course, makes, let's say, things somehow easier in some sense. Okay, let's go on. Step number 3. We want to study the corresponding Hochschild cohomology, and I would say more than study, we want to compute the Hochschild cohomology. Why that? Because the second cohomology contains obstructions to existence of formal deformations, and H3 contains obstructions to equivalence of formal deformations. But keep in mind that when I say deformation now, I still mean deformations compatible with reduction. So really we are studying, we're computing what are the obstructions to existence of deformations which are compatible with the reduction procedure. And at the very end, I will show you something about the work in progress. So the Hochschild constant Rosenberg theorem, which gives us the cohomology at every level, in a particular case, of course, for a particular coisotropic algebra. Okay, so let's start now with, let's say, the proto example we have in mind. So we want to understand how to cook up a definition of a coisotropic algebra, starting, of course, from a coisotropic reduction. So what does it mean? It means that I start with the usual classical coisotropic reduction, meaning I have a Poisson manifold, which is this white box. And then I have a coisotropic submanifold inside, which is this green one. And coisotropic submanifold, if you're not familiar, just think of it in terms of its characterization. So the subalgebra of the smooth functions on the manifold vanishing on the coisotropic on submanifold is closed under Poisson bracket. This is, let's say, the characterization of coisotropic. And then we have a characteristic distribution, so this blue one. And now we can perform reduction, meaning we can quotient out C out with D. And we have again a manifold, and even more, we have a Poisson manifold. And let's say, I mean, the most classical example we have in mind, is of course Marsden-Weinstein reduction. And in this case, C, the submanifold, is actually given by obtained by Hamiltonian actions, meaning we have a Lie group action, so a Lie group acting on our manifold, allowing a momentum map, equivariant, and then C is given as a pre-image of a regular value of the momentum map. So in this case, the characteristic distribution is very easy. It's really given by the orbits of the action. So means that when I go to quotient, I really quotient by G. by the Lie group. This is, let's say, our proto-example, but let me just mention, let me stress that there are more examples of coisotropic reduction. So, coisotropic reduction is really a generalization, I would say. Okay, let's see what happens now if I want to pass from this story I told you to a more algebraic description. So how can I translate? So I have a manifold, a Poisson manifold, and from the algebra side, I have a Poisson algebra. So I have smooth functions on the manifold, standard product, pointwise, plus the Poisson bracket. Then we had the characteristic distribution. And this, if I want to translate in the algebra way, this is very easy. I mean, we have just functions on the manifold. And when I do restrict these functions to my submanifold, and I make the derivation along the distribution, I get 0. So they are constant along the leaves. So this is actually a subalgebra. And this is important to keep in mind. And in the case of Marsden-Weinstein, for example, this is very easy. These are the G invariant functions. So they are really a Poisson normalizer. Then we have the coisotropic submanifold, algebraic description, vanishing ideal. Okay, so it's nice. We have our reduction in terms of manifolds, so in the geometric sense. But here we can also define a reduction of our algebra. So I have a big algebra of functions on the manifold, like a reduce, meaning I can take this subalgebra and quotient out by the ideal. This is a reduced algebra, and even more, what is important for us, this is isomorphic as a Poisson algebra to smooth functions on the reduced manifold. Okay, so far so good. So how can we actually, I don't know how to say, summarize what do we have? I mean, what are the important algebraic ingredients that I need to cook up a reduction in the algebraic sense? Essentially, I need a big algebra, a subalgebra, and a two-sided ideal. And then, okay, in the Poisson case, we have more. We have that this is actually a Poisson algebra, and the reduced one is again a Poisson algebra. But let's stay very general. Big algebra, subalgebra, two-sided ideal. That's all I need. So that's why I give you this definition. I give you the definition of coisotropic algebra exactly like this. A coisotropic algebra is a triple with a total component, AT, a normal component, I mean, really sticking to the ideas coming out of the coisotropic reduction. So normal component and vanishing component, so A0 component, where AT is the big algebra, so an algebra. Generally, we do consider unital and associative. AN is its subalgebra, and A0, sitting in AN, is a two-sided ideal. And with these objects, I can show you, I can cook up a category. So these really form a category, of course, with suitable morphism. I don't want to be too much detail. Just keep in mind, let's say, the philosophy. So morphism here has to be a couple of morphisms. So morphism on the total component, morphism on the normal component. They have to be somehow compatible, these two morphisms, with the injections, and then you need to somehow preserve the ideal part. So this is morally what we need to have in mind. But anyway, I mean, we have a suitable notion of morphism, so we form a category. And this is nice because we can reinterpret reduction as a functor, right? I mean, we can really construct a reduced algebra, and this yields a functor. Because I can say, I mean, a functor takes an object in this category, meaning a coisotropic algebra, and gives me an algebra reduced, which is just the normal component modulo the vanishing component, the zero component. And again, of course, in the Poisson case, this is even more. This turns out to be even a Poisson algebra, but in general, we don't care. I mean, we just stay very general. So this is the reduction that we want to, the factor that we want to consider at the moment.
Chiara?
Yeah.
But this is now both classical and quantum, or is it like?
It is both classical and quantum, and well, I will show you precisely what I mean because I will present you the BRST example at some point.
Okay, thank you.
But yeah, the idea is exactly that. I mean, I have algebras and I don't care, maybe commutative, maybe not. I didn't say much, right? So I want really to recover everything. And then I want to go to deformations. So I just, I don't know how to say, give you a very, very, very brief summary of what is deformations of associative algebras. Why that? Well, first, because I showed you that this triple starts with the unital associative algebra. So when we want to deform this triple, of course, the theory of deformation of associative algebras will enter into the game. This is something we can, of course, already say. We can say, well, I can show you that this is actually a bit more than that, but still, I mean, we need that, and we need some vocabulary. So just to remind you what are the crucial ingredients in this theory. So you start with an associative algebra, and then you want to deform it. Meaning what? Meaning that you consider formal power series on A, and a product which is a deformation in the sense of formal power series. So you start with the usual product on A, and then you deform. So you add a formal power series of B differential operators. And of course, you ask this new product to be associative again. So what is the DGLA governing such deformations? It's the Hochschild one. So we have the Hochschild complex, meaning homomorphism on this algebra. And then we have a Gerstenhaber bracket. If you're not completely familiar with this structure, just keep in mind what is morally the Gerstenhaber bracket. So on homomorphism, you can define a product which is simply concatenating homomorphisms. And then what you can do is just considering the graded commutator out of this product, and that's the Gerstenhaber one, the Gerstenhaber bracket. And then you have a differential, a graded a differential on this graded vector space. Again, I can give you a big formula, but I mean the easiest way to define it, to describe it, is via the Gerstenhaber bracket. So you have just delta described as the Gerstenhaber bracket of the product. And this, let's say, formalism, this chain complex, co-chain complex, help us to rewrite associativity in another way, really by using these structures. Because M is associative if and only if the Gerstenhaber bracket of M with itself is 0. And when I do deform it, the associativity of the formal deformation, it's associative if and only if this part, the deformation part, is actually a Morer-Cartan element of my complex, of my DGLA. So again, I want just to enlighten you a little bit. I mean, show you what is what are the main ingredients of this game. And then at some point you can say, okay, but maybe I do get different ones, but they are still equivalent. And indeed, you can somehow define an equivalence relation of deformations or formal deformations that I will show you better in our case. But just keep in mind, you can have something like a suitable automorphism that connects two deformations, and this really defines an equivalence relation. So at the end, quotienting out the Morer-Cartan element with this equivalence relation, give us an equivalence class of deformation, formal deformations of my algebra, of my associative algebra. And more or less, I mean, this very short recipe I gave you is the one that we will apply for coisotropic algebras as well. Okay. So that's what I want to do, right? I want to now take coisotropic algebras, which are these triples, and I want to deform it. And I understood that I need a suitable DGLA notion. And of course, I would like to cook up a functor, a deformation functor in this setting. So how can I do that? So first, I need to introduce a notion of coisotropic differential graded Lie algebra. So how to do that? So we define a coisotropic DGLA, which I call G, as a pair of differential graded Lie algebras. So somehow the usual moral, a total component, but now the total component is not just an associative algebra, it's a DGLA, so with its structure. Then I have a normal one, same stuff, DGLA structure. And as before, I want Gn to sit inside Gt, right? So as in the coisotropic algebra case. So again, I consider an injection of Gn into Gt, but it has to be also a morphism of DGLAs, so preserving the structures. Third ingredient, we want an ideal, right? In this case, of course, cannot be, an ideal in the sense of algebras. It has to be more, it has to be a Lie ideal and graded because we are in graded vector spaces. And we ask the differential to preserve, the differential over the n part to preserve the ideal. Here there should be a +1, sorry. Okay, so we have, sorry?
Chiara, maybe I can maybe I'm a little bit confused, right? So I understand why we need Gn and G naught, right? Because you're going to use them in the definition of reduction.
But you don't see why you will need the G total.
Yeah, that's right. That's right.
I know. Well, I think the best way to answer you this question is really the very end of this talk, because you will see that when I try to describe in particular the cohomology, the total component really plays a role, really contains important information.
All
So
right. So yeah,
be patient, and then we can discuss a bit more at quite at the end of the talk.
Okay. Yeah. Thanks a lot. I'll be patient.
Excuse me. Could I ask a question?
Sure.
Is it okay? So one way to rewrite your definition would be simply that there's a map from a surjective morphism from Gn to G reduced. By definition, G0 is simply the kernel of that map. So a different way of thinking of this is that you have Gn mapping to G reduced and to Gt. So my question is the following. So I do a lot of work in derived geometry and homological algebra. And essentially, your condition here on G reduced is that the morphism from Gn to G reduced is surjective. And that is a condition which, in some sense, isn't appropriate for working in homological algebra. In homological algebra, you might want to use some sort of notion of some derived notion of surjectivity, but actual surjectivity of the actual complexes is somehow not
inappropriate in the sense that this is too restrictive, you think?
Well, it's somehow not expressible. It's not invariant under quasi-isomorphism. And one prefers to stick to notions which are invariant if you replace your structure by a quasi-isomorphic one. That's all. It's just a comment, but if I thought maybe you have
it's very interesting because reduction of coisotropic DGLAs in the way I will just comment more, preserve quasi-isomorphisms.
But surjectivity is not preserved.
Yeah, I see the point.
That was my point. And so it becomes harder to understand.
Yeah, I understand.
Yeah. Okay, I'll just leave that thought in the air. Maybe we can talk about it.
Thanks.
Yeah.
Okay, so we have this definition. As I told you, trust me that the total component has something inside. And this, of course, defines a category as well. So again, we have a morphism suitable, which is pair of maps. I mean, you got the idea, right? I mean, the morphism have to be always the same. I mean, connecting total and total, normal and normal, preserving the ideal part. So that's always more or less the idea. Okay. And for example, an interesting example is just you can take derivations of coisotropic algebra, and you have really coisotropic DGLA out of that.
I am sorry for interrupting. May I ask another question about the definition? Yes. So this map I here, do you assume anything about it, like that it's injective on cohomology, for instance, or like that?
No, not at the moment. No.
Okay. And then so another question. So is it possible to from this data that you have here, from this pair of DGLAs, morphism, zone, and ideal, could you construct a single DGLA out of it by forming some kind of semi-direct product, or
by reduction set? Yes.
Huh?
Via reduction, yes. For example.
No. Before you do the reduction, I mean,
so
I think what I'm trying to say is that, well, according to the general philosophy of deformation theory, there should be a DGLA governing any deformation problems. I mean, you described a deformation problem, and now you describe something that's not just a DGLA, but I don't know.
Yeah, it has more.
So there's some more complicated.
Yeah, more complicated because it has more.
Can you take all that and convert it into a single DGLA, which governs the same deformation problem?
I don't know, to be honest. I would say no. But I don't know if we can. I don't know to say summarize in a single one.
Okay, thank you.
You're welcome. Okay, so the comments I wanted to make, as you can see, is first, of course, everything can be extended to formal power series, just lambda linearly, and that I can do reduction as well in the usual way. So just Gn modulo G0, this is a reduced one, and this is a DGLA. So again, we have a reduction factor from coisotropic DGLA to DGLA. Okay. And now, of course, as I did before, I showed before, I need to understand what is a Maurer-Cartan element for this new DGLA, more complicated DGLA structure. So before doing this, I have to introduce you a new, another algebraic notion, which is the notion of coisotropic sets, because you will see that Maurer-Cartan elements really form a coisotropic set. So coisotropic set just mean a pair of sets, again, total normal, plus a map from Mn to Mt, and then we have an equivalent relation on Mn. So these again allow us to define a reduced one. So we can just quotient out Mn with the equivalence relation. So this gives back a set, of course, and then we have a functor, also in this very generic setting. And now we see what Maurer-Cartan elements are. I mean, G, remember, is a coisotropic DGLA. So what do we have? We have the Maurer-Cartan element of the total component, which is a set. Maurer-Cartan elements of the n component, again a set. Of course, we can get a map from MCGN to MCGT out of the map we have from GN to GT. And then we have an equivalence relation. Very easy. Keep in mind you have this graded Lie ideal. So we can say two elements in the normal part are equivalent if and only if the difference lies in the ideal. So you see, I mean, we have actually this coisotropic set structure. But this also means that we can look at Maurer-Cartan again as a functor. So from coisotropic DGLAs to coisotropic sets. So we are really going in the direction of defining a deformation functor. Now, I don't want to introduce you another coisotropic algebra structure. Just, let's say, believe me that we can define a suitable notion of coisotropic groups and a suitable coisotropic group out of a DGLA, or coisotropic DGLA, plus a gauge action. So this group, this coisotropic group, acts on Maurer-Cartan elements, and this implies the fact that Maurer-Cartan elements are equivalent if they lie in the same orbit of the action, exactly as in the classical theory of deformation of associative algebras. So we can define now, let's say, a new coisotropic set. So deformation of G total component, which is Maurer-Cartan elements, of course, of the, as I said, the extended version of the coisotropic DGLA, total component, modulo this gauge action. Total component and component. And then we get also an equivalence relation out of the equivalence relation we have on the Maurer-Cartan elements. So we have two equivalence classes, are equivalent if and only if the representative objects inside are equivalent in the sense of the Maurer-Cartan. So you see, we got at the end a deformation functor. So from coisotropic DGLAs to coisotropic sets.
Chiara, maybe I haven't got it. How is it? So you have a Maurer-Cartan element for T and for N. What about for G naught? What happens with G? How does this one deform?
For the zero component. No, the zero component enters in the game only to define the equivalence relation.
Oh, but in principle, it should be right a DGLA, which may also be deformed. And now you're saying the two deformations, the deformation of GT and GN, do not quite agree exactly on G naught, right?
Say again, sorry.
So the two deformations, right, described by the MC elements, they don't quite agree exactly on G naught. So what's the result of this deformation? What is the new G naught after I deformed?
Okay. Wait. Okay, I understood it. Okay. So let me try to go a bit further so you can see exactly what happens in the special case, because this is to me still very, very abstract, and I think this makes some confusion probably. Because of course you can say, okay, that's a definition of deformation functor, but I don't see how this can be actually related with the formal deformations in the sense we have in mind. But first I have to show you what a formal deformation of coisotropic algebra is. So a couple of slides, so you will see why this actually matches. Okay?
Okay, thanks.
Okay, so, well, let's say, let me first answer another question. And the question can be, okay, you told us that you want to study deformation and reduction. Now, what's happening here? I mean, and the first result here is the following, that in some sense, deformation and reduction do commute in the following sense, that you have, there exists an injective natural transformation eta from coisotropic sets to DGLAs, making this diagram commute. So making the diagram deformation reduction really commuting. So you see, I mean, this shows us that somehow this formalism of coisotropic DGLAs, coisotropic algebras, is really somehow compatible. Well, it's really encoding reduction, and these deformations are somehow compatible with reduction. But this will be even more clear afterwards. So let's say now we have really to understand how to connect this abstract way of deforming via functor with the formal deformations I have in mind. And I think this starts clarifying a little bit Anton's question. We have to understand which coisotropic DGLA actually controls the formation of coisotropic algebras. So we have our coisotropic algebra, meaning we have this triple of algebras, and a formal deformation of it is given by a multiplication on the total component formal power series, associative, such that it can be rewritten as we did before, right? So because A total is really an associative algebra, so we really look at deformations on it in this sense, in the usual sense. So formal power series of B differential operators, right? And then we want to somehow preserve the coisotropic structure. So AN was a subalgebra of AT, and now even though we deformed AT, we want AN formal power series still to be a subalgebra, but keep in mind that AN is still undeformed. And the very same for A0. A0 was a two-sided ideal. We want to keep this. So has to sit inside AN formal power series, two-sided ideal, again undeformed. Okay, so this this is a good moment to show you first the example. As Anton was mentioning at some point, this is really recovering the quantum setting as well. And this we can see, for example, we can recover BRST reduction. If you're not familiar with BRST reduction, just keep in mind you have your Poisson manifold, you have your Hamiltonian action, which is, again, Lie group action acting on a manifold, allowing an equivariant moment map. And then we can actually cook up a coisotropic algebra. So smooth functions on the manifold, the Poisson normalizer over C, which is, remember, the pre-image of the regular value of 0, and the vanishing ideal. And now we assume we have a star product on M, which is actually G invariant, which also admits a momentum map, but a quantum one in the sense of, again, sense of deformation quantization. So you have your classical momentum map plus some formal power series. And now this is clearly now equivariant with respect to the star commutator and help us to define a new coisotropic algebra. And this algebra now, as you see, the deformed total one. And then you have the quantum vanishing ideal, which is the kernel of this function, this map, sorry. So the classical injection composed with, well, let's say a suitable S, meaning identity plus formal power series of differential operators. And this is such that IC is a left ideal, remains a left ideal, with respect to the star product, of course. And the BC is just functions whose restriction to C are G invariant. So, of course, out of these ingredients, as we've seen, we can cook up a reduction. So BC modulo E, the ideal. So in this sense, you can see that coisotropic algebras recover the quantum case. But what is more important in some sense is the fact that we can see that the deformation of the classical coisotropic algebra, A, a formal deformation of this, is actually isotropic to this one, to the coisotropic algebra, I don't know how to call it, bold A. So it's really something, yeah, recovering the cases that we want to recover. Okay, now let's go to let's say the most complicated part. But in this part, you can already see a little bit, I can already start commenting a bit what happens with the ideal part and with the total part. So it's still, I mean, we are going a bit in the direction of the questions I want to. So I will try to really give you a rough idea of how to describe a coisotropic Hochschild DGLA, not to be too much, too technical. But let's start very easy. We have our coisotropic algebra, right? So this means that we have AT, which is a total component. Start with this, associative algebra. So we can cook up the usual Hochschild complex, this one. Then what we have to do is obtaining a normal component, so because we have this structure of DGLA, of coisotropic DGLA in mind, so we need a total component, a normal component, and let's say a zero component, right? And okay, the total one is easy. The normal one cannot be simply CK of AN. We want to get a subcomplex of the total component. We want to get a sub-DGLA. So we want something which is somehow non-trivial, because otherwise this would be, you understand, this would be simply, I don't know, putting different Hochschild complexes in a triple. Not very interesting and not very rich, because we will see that actually this way contains much more information. So I define the normal component in this way. Let's say the philosophy I have in mind is that I take the homomorphism on the total algebra, and I want to have some kind of normalizer behavior in some sense. So if I inject k times the n component, then I still remain in the homomorphism. I still remain in the n component. And you see, I mean, if I inject once the vanishing component, I still remain in the vanishing component. So ideal behavior in some sense. So we have these two pieces, and then, well, again, of course, I need an extra ingredient, which is the vanishing one, the 0 one. And this you can think as couples of homomorphism in the total and normal component that somehow move from n to a 0 component, morally speaking. Okay, but let's say the most important part, and you will see why this is, I mean, this is really the crucial, you understand that this is really the crucial ingredient to study reduction and to study compatibility with reduction, is the fact that this is a subcomplex of CK of the total component. So what do? We just define the Hochschild differential delta, essentially given by the total one. Here we have the usual one, usual Hochschild differential, and then we simply somehow restrict to n, and then we restrict again, and we get the differential I want on the vanishing part. And the very same for Gersten-Haber bracket. I mean, we start with the Gersten-Haber bracket on the total component, and then you restrict in the normal component. So we get really a subcomplex and a sub-DGLA. This clearly means that we get, I mean, we have a differential, we get a cohomology, okay, in the usual way. So we make this the usual quotient, but now if I want to write it explicitly, you know, I mean, when I compute, when I look at cohomology, Hochschild cohomology is still a DGLA. So in this case, should be still a coisotropic DGLA. So again, we have total component, which is clearly the classical one, right? Because it's just the Hochschild cohomology of the total component. But when I go to the normal component, then it's a bit different, because this is really the kernel of the restricted differential. And again, also for the zero component, we have something different. We have to restrict and restrict. And so this gives us something different. And I really want to remark that here, the total component do play a role. And this you will see. I mean, when I will compute the cohomology, in the case we are interested in, you will see exactly that this is really something that contains information about the deformation of the total algebra. So this is really something that plays a role, even though in the reduction, it's true, I mean, we only use the normal and the zero component, but still this is important. This contains some information. And now we can wonder again what happens. I mean, if, let's say, this notion of Hochschild cohomology, this coisotropic Hochschild cohomology and reduction behave well each other. So we could prove first that we can look at the Hochschild cochain, let's say, again as a functor. So you take your algebra and you get your Hochschild DGLA. And the very same at the coisotropic level. You take your coisotropic algebra and you get your coisotropic Hochschild DGLA. And then reduction works at this level as well, so vertical arrows. So again, this diagram somehow commute. There exists an injective natural transformation making this diagram commute. But more important for us, when we pass to cohomology, we have the same diagram, meaning that if I look at the reduced DGLA, coisotropic DGLA, okay, the Hochschild cohomology is again a DGLA, a Hochschild one, coisotropic one. This sits inside the coisotropic, the Hochschild cohomology of the coisotropic algebra, reduced. So this also shows a little bit why I say that this is actually containing information. And then usual sport. So how to describe formal deformation of a coisotropic algebra? I can reinterpret in terms of Maurer-Cartan elements, meaning that a multiplication written in this way, so the undeformed part plus a deformation piece, which is formal power series, of course, is a formal deformation of M0 if and only if it satisfies a Maurer-Cartan equation. And this is very easy to show, as usual, I would say, as in the theory of associative algebras. And then we can see, I mean, again, we can define equivalences. We can say two deformations are equivalent if there is a suitable automorphism relating them. But in this case, we can say even more. We can give a characterization. So we can say two deformations are of a coisotropic algebra are equivalent if and only if there exists a coisotropic homomorphism inside this formal power series, such that I can connect M and M prime via this action. So explicitly, this means, again, of course, we have a total component and a normal component connected by this action. And this, I mean, this is the total component of the Gersten-Haber bracket. This is the normal component of the Gersten-Haber bracket, meaning, as I say, the restriction of it. And there you see, I mean, we can really see, say, the set of equivalence classes of formal deformations of a coisotropic algebra obtained by using this recipe coincides with the deformation I gave you before. So the deformation I gave you before was just, you remember, Maurer-Cartan element modulo the gauge action, total and normal component, and the equivalence. And we can see that they really coincide if we take as a DGLA the Hochschild one. let's say, as in the usual case. But here we have to keep in mind that, again, we have more information. So it's not, as I said, it's not just putting the deformations of AT, deformation of AN, parallel, untouched each other, and putting in a triple. No, we have more, because this really contains more information and they talk each other. So the total component really plays a role, and the zero component really plays the role of the equivalence class, because remember that this is now a set, I mean a coisotropic set, right? This is not a DGLA anymore. So deformation factor goes into coisotropic sets. And then, of course, we want to see what are the obstructions for such deformations. And as we can expect, the obstructions for deformations of coisotropic algebras are really given by the third Hochschild cohomology and component. So as we said before, the normal component is really important, really plays a crucial role in this, is the one somehow describing the obstruction for deformations which are compatible with reduction, as we said. But the whole object, so H83, the DGLA, let's say, contains more information. The total component, keep in mind, is the same as the Hochschild component and the Hochschild cohomology of the total component of my coisotropic algebra. So it really means that we are describing also obstructions for the deformation of the total algebra sitting inside our triple. And what about the zero part? The zero part is also important because, of course, I mean, when we go to reduce, right, we have to quotient out with the zero component. So somehow we can have the intuition that this is really controlling which obstruction on A descend to obstruction on the reduced algebra. So this is really the role we have to keep in mind. Okay, and now, you know, I mean, I hope I convinced you that the Hochschild cohomology of such objects is interesting, is nice, and we really want to compute it in the case we are used to, let's say, I mean, in the geometric case. So let's just remember what happens with the HKR theorem when we have the algebra of infinity smooth functions on the manifold. The smooth version of the HKR theorem tells us that if we compute this cohomology, I mean, this is of course restricted to differentiable ones because we are in the smooth case, well, then this is isomorphic as a Gersten-Haber algebra to multivector fields on my manifold. So we would like really to compute and to prove a coisotropic HKR theorem. In the case of really, as I said, in the geometric case, so we really come back to the coisotropic reduction setting in which we have a manifold, a coisotropic submanifold, and a characteristic distribution. This defines a coisotropic algebra, as we have seen before, total algebra, right? Functions constant along the leaves, and the vanishing ideal. This is our coisotropic algebra that I from now on I call infinity of this curly n. And we really want to compute the Hochschild cohomology at every level, at every degree. Normal component, as I said, of course, because this is the important object for us. Okay, and now, well, let's say, what's the state of the art? The state of the art is the following. So we could compute the first one, the first coisotropic cohomology. which is nice. Of course, this can be easily interpreted as derivations, outer derivations, compatible with reduction. So we computed it. And let's say it's not a big surprise what we got in some sense, because we got vector fields, you see, tangent to C essentially. And okay, because you see, I mean, these are really vector fields. And when you make the Lie derivative along the distribution, you still stay in the distribution. And this means essentially derivations of this coisotropic algebra n component. It's true. I mean, this is somehow something we can expect, because as we say, the interpretation that we had in mind was derivations compatible with reduction. But it's important to notice that this is not the derivation of the n component of the coisotropic algebra. So again, I'm not, putting in a triple all the objects independent of each other. This is something different. And then we can go to the second cohomology. But here, so far, we could only compute the local case. I want to show you a little bit what is the result in this case. Also because this somehow explains what's next. So local case, so we are in Rn essentially. So this is, let's say, our triple, right, of manifolds. So manifold, submanifold, and ideal. This is very easy to get a coisotropic algebra. And then we want to compute the second cohomology. This will be very important because again, the normal component, I mean, because this will be interpreted as infinitesimal deformations compatible with reduction. But then when you go to compute this object, you can see that this is something more complicated than expected. And this somehow comes also out of the fact that I was telling you that I'm not just, putting in triples, these Hochschild cohomologies. Why I say that this is something a bit more complicated than expected. Let's say, well, analyze roughly what we got. First piece, okay, no surprise at all. Okay, bivector fields, okay, as expected. And which bivector fields? I mean, the two legs of the bivector field are on the n component, so they are the compatible with reduction. Okay, so this is very expectable. But then we have already here something funny, because we have again a bivector field. But then you can see the first leg is simply whatever. So the first leg is whatever. So the second leg, yes, is compatible with reduction. I mean, if you really go to, and you pass to reduction, this get killed. So it is okay. I mean, it's enough to work, let's say. But already it's something new that you don't have. I mean, not new. I mean, it's something like richer. You don't really have two legs both compatible with reduction. You just have one leg. And then you have this extra part, which you can have in mind something like this is a bidifferential operator, but you see this is not skew symmetric, this is not anti-symmetric, this is actually symmetric. And this is, okay, a bit harder to interpret, but I just want to show you that you see, I mean, this cohomology, this second cohomology is compatible with reduction as we proved, but this is somehow harder, richer, because of what I say, because this is not just piling up stuffs. Okay, so time to finish this with the outlook. So what next? What's the project now? So of course we would like to compute higher cohomologies in the local case. But more interesting, we want to go to the global case. And there I can tell you, I mean, we have already some results, But what I want to mention here is that we cannot simply glue together the local results. We really have to handle with the invariant partition of unit. I mean, this is not something we can just glue. We have really to work at the global level and to cook up a proper calculus on this to do that. And then, of course, I mean, once we will have the HKR theorem, the natural direction, of course, if you know a little bit of formality, is going toward a coisotropic version of the formality theorem, because HKR is somehow a first step for the formality theorem. So in this case, we could be able to write a formality theorem that already encodes the informational reduction. So in some sense, we are trying to approach the deformation and the quantization and reduction diagram with this approach from this point of view. And with this, I will stop. So thank you for your attention.
Thanks a lot. So please, questions or comments, you can either unmute yourself or raise your electronic hand. So let me start with one possibly naive question. So, right, there was this inclusion of the reduction of Hochschild cohomology.
Yeah.
Was a subset or whatever, was a subgroup of Hochschild cohomology of the reduced algebra, right?
Yeah.
Could you say a little bit more about it, in the sense that, like, okay, maybe naive expectation would be that they should be equal.
Yeah, this would be
right, but they're not equal.
They're not.
Does it mean something in particular? Why? I mean, does it mean maybe that our definition is wrong, or does it measure something with difference? Maybe you, yeah. Could you say something about it?
Well, in some sense, well, we were thinking about that, and in some sense, I think we can interpret this by saying, I can say something like the information inside the reduced DGLA is somehow contained in this one, and this is somehow something, I don't know how to say. Maybe we can expect something like this, because what you're doing is really trying to again to get something which is more constrained, right? I mean, this is just Hochschild cohomology of an associative algebra at the end of the story, and that's it. And here we have more. Here we have all the procedure inside. I mean, because this is a triple, and this is then reduced in the algebraic sense. So to me, it's something we can interpret in this way, that you're adding some more constraints. So in this sense, you can expect that this is somehow contained inside. You see what I mean? I'm trying to give a little bit heuristic explanation, of course. I mean, to me, the definitions so far are quite stable, because they recover all the examples we had in mind, not just BRST. I mean, we have, of course, the usual coisotropic algebra. We have the Poisson-Lie group case. I mean, all the cases. And even just imagine you have just a manifold and a foliation. Done. You have a coisotropic algebra, and you can deform it with that techniques. So I think you can interpret this way, in my mind.
Okay, thank you. More questions or comments?
I think Jonas Schnitzel has a question.
Mm-hmm. Yeah, please.
Hi, Chiara. I have very, probably it's more a comment than a question.
Mm-hmm.
the Hochschild cohomology seems like there are some error terms coming from this coisotropic stuff. But you're trying to compute something which already is non-trivial Hochschild cohomology. So probably if you, or do you know if you can compute, for example, let's say the local Hochschild cohomology of the continuous functions on any space, which should be trivial, but if you put this, is there something left over which you don't see in the, if you just take the classical?
I see your question. No, I don't know actually. I mean, so far the computations we have is the one I showed. So the continuous case, no, we don't think about that actually. But you're right, probably this can show something that you cannot actually, see in the smooth case. I mean, of course, we were interested in the smooth case.
Yeah, sure. But what can happen is that your usual Hochschild cohomology is just vanishing, but you still have the coisotropic one by just taking, I don't know, a topological space, a subspace, and taking continuous functions.
You can see more in this sense. I see your point. Yeah, I will try to discuss this with Marvin. Thanks.
Thank you. More questions? So I maybe got another question. So you mentioned Poisson groups. So what could you say a couple of words? What happens? Kind of how do you see Poisson groups in that context?
Yeah, Poisson groups. I mean, I just mean that the usual reduction, the one defined by Jean Gualou, can be also rephrased as a coisotropic reduction. And even more, I mean, this is long ago, but I also, out of this Poisson-Lie group action, you can somehow cook up an infinitesimal action of Lie algebras on Poisson manifolds. And this gives you a reduction of the tangent bundle. And this reduction of the tangent bundle, we could prove with the coisotropic technique, the usual one. So this is again a coisotropic reduction example, and this we could recover by this language.
Okay, thank you. So more questions or comments for Chiara? Well, if not, thanks again.
May I?
Sure, yeah, please.
Yeah, please.
Yes, so just recalling some work by Frege, Mark, and Yao. I think I was just looked it up on deformations of diagrams of algebras, which I think might be relevant.
Diagrams of algebras. Okay.
Yes. Well, the simplest case of that would be just a single morphism between two algebras. And in your case, it's well, you have two. You have a subalgebra, so one algebra mapping into another, and then that algebra also mapping down to the reduced one. So it's a diagram with two legs, like a span. Yes, so there's been some work on the problem of deforming, of deforming such diagrams, and that's actually,
can you say again?
It's kind of non-trivial because it leads to an L-infinity algebra governing deformation.
Okay, yeah. So
so it's just something that I think maybe might be relevant to what you're trying to do.
But thanks, yeah.
So it's I think Martin Markle and Frege done work on that.
But there's also much older work. Sorry to interrupt, but I just want to add there's much older work of Gerstenhaber and Schack.
Exactly. Yeah.
They studied general diagrams, and it really feels to me like what you're looking at is deformation of spans, and that your main theorem might find some I mean, the interest of your theorem, I think, is geometric, but
Yeah, sure.
the technical details of finding out what it is that you want to study could be possibly hidden in the work of
Many thanks.
these two collaborations, Gerstenhaber and Schack and Marco and Fourier. Yeah.
Many thanks. That's very interesting.
Ellie?
I just wanted to point out that I have a somewhat recent paper on diagrams of algebras and the Hochschild complex and the L infinity algebra there. So I have a different proof of some of the Gerstenhaber and Schack stuff, and I have a construction of the L infinity algebra, which, reproduces the Markle et al. Stuff is a special case, but it could be applied to the span diagram, and that would be interesting.
Cool, thanks.
Right, thanks a lot. More questions? You know, when I try to close the session, you come up with more questions, right? So it's stimulating. I can, if you want, I can try again, hoping that you would. So if there are no more questions now, well, I don't know whether this magic works for the second time. Right. So Chiara, thanks a lot.
Thanks a lot.
Thank you again. Right. So thank you everybody for participating, and we'll meet in 2 weeks from now on Global Poisson.
Okay. Many thanks.
Yeah, thank you. Bye-bye.
Bye.